We're very happy to present our first place solution today with all the audience. The team was Darragh and myself. Can you go to the next slide? So we quickly give an introduction of ourselves, summary of our of the competition itself, a summary of our solution, then talk in more details about model and training methods, and at the end give a quick ablation study just to show what key points were necessary for our solution. So I'm Christoph Henkel. I work at NVIDIA as a senior deep learning data scientist, and I'm part of NVIDIA's KGMON team, so which is all Kaggle grandmasters. I have a PhD in mathematics, and I'm currently ranked #1 in the world on Kaggle. So I have quite some experience in all deep learning related fields, so computer vision, NLP, speech recognition, and now also sign language recognition.
And I'm Darragh Hanley. I'm an AI research engineer at Doubleyard, which is a part of the EduLab group in Japan. And I have a BA in engineering and mathematics.
Yeah, and on the slide before, there was some comment that we participated also in the first round of the competition, so the isolated sign language recognition, and we finished in 2 separate teams in like 6th and 8th place. So we already had some experience with a very similar data set, and that quite helped getting us up to speed in this competition. Next slide. So I can very quickly go through this one because you all know the data, you know the task. Anything I want to add from here, which you don't know, probably everything you are familiar with. So I guess we can skip on this slide. So the main challenges for us in this competition was that a lot of the data samples were just like not usable, like 10 to 12% were just very small sequences where people probably just tap the record button. I found it interesting that you left this data in. So I think it's always better to leave like noise within a data set and have like competitors working on it and working out what you can do with it. But that was quite some challenge for us. And it also leads that the theoretical maximum of score probably is around 0.9 if you ignore like those nonsensical data ones. Then for us, it was quite challenging because we don't know TensorFlow. So we are very familiar with PyTorch, and everything we do is in PyTorch. So when I started Kaggling, I started using TensorFlow back in the days. So it was quite interesting to refresh my knowledge of TensorFlow. And especially since we very early on took the decision to port everything one-to-one from PyTorch to TensorFlow line by line, that really helped us to understand every line of the modeling and masking we were doing. And additionally, the constraints in model size and runtime was also quite an interesting challenge compared to other Kaggle competition, because that puts more focus on computational efficiency compared to other Kaggle competitions. So for cross-validation, we did the same as in the first round, namely split by signer, which we thought is what the organizers did in the dataset. It has nowhere confirmed nor denied that this was the case. But at least for us, splitting by signer gave a very high correlation between our local cross-validation and the leaderboard. We split by 4 folds, but mostly use just the single fold for validation, just because it's like faster to train, and it's significant correlation between this approach and the leaderboard. And then for the final submission, we fitted a model with the same hyperparameters just on the full data set. That gave some additional boost. For preprocessing, we normalized per sample, very similar to what we've done in the first round. Fill the nons where no landmarks were visible with zeros, and we interpolate sequences that had more than 384 frames. And if they were shorter than 384 frames, we padded for training, but did nothing for inference. So if a sequence was very short, since in inference we had a batch size of 1, we could just use this very short sequence as is, and this gives quite a significant boost in computational speed. This slide just gives a small overview about the Mediapipe model, which you also might be aware of. I think the core takeaway is that parts of our solution address how Mediapipe is working and shortcomings from the Mediapipe landmark identification, namely that you have like 3 models which are like sequentially inferred. So first you like get a pose, and then from this pose you crop a hand and you crop a face, and you have like 3 different sources or 3 different models which you aggregate to extract landmarks. And it's at least in my opinion important to keep in mind how Mediapipe was like extracting the landmarks.
So I'll go through quickly the augmentations. I think if we look through the augmentations, like we've got the standard augmentations used for speech recognition. I think the 2 types of augmentations we introduced additionally for finger spelling, which was quite strong, was dropping out fingers. So randomly dropping out certain fingers, just zeroing it, doing the same for pose or face or hand. It seemed to help the model be more robust, and also the time shift. So doing these over certain times helped a lot, as opposed to just dropping out for the whole video, or the whole I guess that's what it is, video. And we show how this dropping works out here, how it would actually look if you were to visualize it. And what I didn't mention, we also used outer cup mix, which is taking part of a video from one person and taking part of the video from one person and the end of another video from one person and stitching them together. And what we do is we take the text from the first part of the video and the text from the last part of the video and stitch them together, and then put that in as a new sample. And this helped a lot to make it more robust. It ran longer, the training ran longer, but it helped robustness.
Yeah, so this is basically our model architecture on one slide, having like 3 main components. One component in light blue is like the feature extraction, which prepares like the input towards and transformer like input, where you have like a sequence of feature vectors. Then you have the encoder, which is like in terms of model parameters, the biggest part. So we have like 14 layers of the squeeze former blocks, which we will explain like in the next slide. And then the third part is like a decoder, which has way lower parameters and is like different to what was like more popular in this competition. So most of the competitors use CTC loss without a specific decoder, but we saw that having like an explicit decoder works better than CTC. So for the feature extraction, Okay, this slide looks a lot, but I can go through it quite quickly. So having the original XYZ coordinates of your landmarks, we select like specific landmarks. I think we use like 168 or so. Use specific landmarks and then just stack the XYZ coordinate like you have an RGB image. So at the end, we have an image with 3 channels, which the 3 channels are like the XYZ coordinates. You have the time axis and you have like the ID of your landmark. And having basically this input, we used as you would use like a regular image input. So we do a 2D convolution on this input to like aggregate points which are close together. And then add a simple batch norm plus activation and flatten out all the resulting features, and then project onto the feature dimension which we use for the transformers, which in our case is like 208 features for the transformer input. 208 is simply the result of maxing the input, which was possible within the 40 megabyte restriction. So that was like the last hyperparameter we maxed out just to fit within the 40 megabytes. And then additionally, we found that we get a slight boost if we split the different body parts up beforehand and have like additional 2D convolutions per body part, which also do per body part normalization. And I think that also helps like additionally to model like very local interaction. So if you have like in this image here, you are interested like in the finger spelling and finger interaction, and you have like a normalization which is happening across the whole body, then this makes like is less accurate than if you just have like a normalization within the hand and do like stuff on this. So that's why we found it's helpful to separate the body parts, do additional normalization by part, and then aggregate everything back together. And so, and the result there was like an standard, in quotation marks, standard transformer input, which is like a 208 feature vector where you have a sequence length of 384. And this goes into this somewhat adjusted transformer architecture. Adjusted meaning that it's like a combination of transformers, so multi-head self-attention and convolution. And we found this architecture very helpful for this kind of speech recognition problems. And the same was true for the first place solution or other top solutions of the first round, that the combination of convolution and self-attention is really key in having an efficient architecture. So we found that squeeze former block, and that's like one squeeze former block, is like the most efficient way in doing this hybrid approach of self-attention and convolution. You can read the transformer paper for more details, but the core is you have a transformer like self-attention plus convolution within the same block, adding some residual units and layer norm and so on. And then we have one block, and we basically stacked just 14 of these blocks on top of each other. Also there we saw having more blocks gives you better results. And by being more and more efficient in terms of computation, we could add more and more blocks within the 14 megabyte restrictions at the end. A core point there was that we also added masking, but Darragh will talk about this on another slide. And then for the decoder, we added one additional augmentation, because normally for the decoding, you have a perfect input for training. So you take the label, you mask everything until the token you want to decode next. And then having this perfect input, you decode the next token. But that's not so robust in terms of inference, because for inference you have like imperfect tokens which have already been predicted. So masking this previous tokens also for training is very helpful for making the model more robust. So that's something we introduced here. I haven't seen this in the literature before, but I saw that another top team did like this. So we had two decoder layers, which were standard transformer decoder layers, and use this for decoding our prediction. What we did additionally, just to mention, we had one auxiliary component, which was taking the one output of the encoder and creating a confidence score. And we used this for post-processing. That gave a very minor boost additionally. And also we had a second backward decoder, which basically does the whole decoding on the backward sequence. But that also gives like a minor advantage, I would say. Not too big.
So, like you mentioned earlier, masking was quite important, and we needed to build this into the architecture. The reason we needed masking is because the model trains on a full sequence and on a padded sequence, and the layer norms and the convolutions learn to have a padded sequence. You can do masking of convolutions in TensorFlow, but we were training PyTorch and it couldn't be done. So we did that there in PyTorch with some custom reshaping. I won't go into how it was done, but it was reshaping specifically for the layer norms and the convolutions to allow them sort of work over just the unpadded data. One of the things we needed to do was pack as much in to the time we had for inference. So speed ups were quite important. We found speed ups by replacing the squeeze former positional embedding with rotary positional embedding. I think the reason this worked here is because we didn't have many frames as would typically be used in speech recognition. Finger spelling has less frames than speech recognition, so we can use that to modify the speech recognition models. So we replaced out those positional embeddings with rotary embeddings. It gave us 2x training speed and 3x inference speed. What we also did was used half precision, FP6 floating point 16 precision, and this helped reduce the model size basically in half as well. Conversion to TF Lite. It was quite a good exercise. I won't go through it all here, but we needed to basically rewrite everything we had done in in PyTorch within TensorFlow. And as Christoph said, this gave a great understanding for where we could make tweaks on the details of the model. It would be a nice exercise to do every time we train the model, because I'd say we get a lot of efficiency speed ups. But you can see it in our code base how this was done and how we converted the model and so on. We also trained in floating point 16, like I mentioned, so we could export the model in floating point 16 as well. Christoph, do you want to?
Yeah, so that's like one slide ablation study. What were like the core points that helped us, and the like in terms of leaderboard benefit. And I think that's true for public and private leaderboard. So the augmentations help quite a lot. especially cut mix and the finger dropout was, so I think finger dropout, we were the only team that used this one. Or a lot of this, the stuff on the slides I saw in other top teams, but I think what separated us from other top teams that we did more of the things. So someone found, okay, cut mix, but not like this, the second place, for example. Someone found masking the decoder inputs and so on. But we found like multiple things that were really helpful. So augmentations, as said, cut mix, finger dropout, phase and post dropout. And I think phase and post dropout was mainly how the Mediapipe model is working. And I don't know if it's like making mistakes every now and then where it doesn't provide like a phase, for example, and we were able to replicate this while training, or it just helps the model to focus more on hands. I'm not sure what was the helpful part, but it helped significantly. For model improvements, there was the CNN feature extraction we used that was quite helpful and was something new compared to the first round. Then having this two branch, so the separation of like the overall feature extraction and then feature extraction for body type. Then using squeeze-former compared to other top models was quite fruitful. Having a decoder compared to CTC was quite helpful. We also tried like a joint approach where we have a decoder plus CTC and we average the losses or weight the two different losses. But decoder only was really like the best way to go, at least in this competition, where the predicted phrases are quite short. I think that's something very important to keep in mind, that the predicted phrases are very short here. And then having a more sophisticated post-processing using this confidence score also helped quite a bit. For efficiency, there was all the things Darragh mentioned gave not a direct boost, but an indirect boost, because a more efficient model allowed us to have a deeper model. And we saw that a deeper model is normally giving you more accuracy. One thing that Darragh hasn't mentioned, but was quite useful, was to establish caching and early stopping in the decoder we are using. That gave quite a speed up, I think like 2x or something in terms for inference. And then having the post-processing by replacing this bad predictions, which I mean like figuring out the 10% garbage data and replacing for those 10% of data where you don't have any signal, replace this with a dummy phrase. That gave like also a boost. But I think that's something most of the teams in like top 20 or top 50 even found. And then one very last experiment we did after the competition, we were interested in how small our model can be and still win first place. So we did some experiments there after the competition ended. And we saw that we can reduce the layers quite a lot and just use a single seed and cut it down to basically 25% of our original model and still end up with a score that would give like first place. Yeah, I think that's it from our side.